So, in the previous lecture we have introduced the concept of countable sets and few examples we have seen the countable sets, all uncountable sets. Here we will continue with the same countable sets with few more examples. So, the first example let us say set of all squares of natural numbers has a number is countable because the set of squares of natural number means it is 1, 4, 9, 16 and so on. That is a set of those element x where x is of the form n square and n is a natural number. Okay. So, this set has a one-to-one correspondence if we define a mapping f from J to this set say capital A, which maps n to n square, that is f of n is n square, then it is easy to show that f is 1 1 and it has a one-to-one correspondence. So, because why 1 1? Because f n 1 equal to f n 2 will implies n 1 square minus n 2 square is 0, which implies n 1 minus n 2 into n 1 plus n 2 is 0, but n 1 plus n 2 cannot be 0. So, this implies that n 1 is equal to n 2. So, f is 1 1. Therefore, there is a one-to-one correspondence between the set A and set of positive integers j 1 to n and so on. Hence, A is countable. Similarly, the other sets are also like set of all even positive integers or set of all odd positive integers or maybe the set of all prime numbers, that is 2, 3, 5, 7, 11 and so on. These are all countable sets. Which can be easily shown by drawing a mapping from this set to the set of natural number, which is easy to just say. Even in positive integer f of n is equal to a mapping can be defined from J to this set say B such that f of n is equal to 2 n. Then this is a 1 1 mapping and into. Similarly, here odd integers 2 n plus 1 and like this. Similarly, for the primes also we can do for that. Okay. So, these are all sets which are countable and it is all subsets of a natural number, subset of the. So, it means this shows that an infinite set is a set which has a one-to-one correspondence with its subsets also. Okay. So, that is why we define like that. Then another examples which we are doing, the set of all rational numbers are countable. Set of all rational numbers is a countable set, and this also we have discussed it that when the positive, let us take the different cases here again. Suppose I take set of all positive rational numbers, that is, it will be of the form p by q, where p and q both are positive. Okay. So, basically this and p q are say integer natural numbers. So, basically this is of the form, if you put it in the form of the sequence, it is of this type p q sequence, where p q are natural number. Then we can arrange in the form of the sequence, we can arrange these numbers in the form of sequence such that p plus q is r, where r is 2, 3, 4 and so on. It means, we can put it in this way 1 by 1, the first term, so that p plus 1 is equal to 2. Then we can put it as another say 1 by 2, 2 by 1, so the 3, and then we can go 1 by 3, 2 by 2, then 3 by 1 and continue this. So, it has a 1 to 1 correspondence with the set of positive integer, which has a 1 to 1 correspondence with the set of positive integer 1, 2, 3, 4 and so on. So, it is a countable set. Then same case is with the set of all negative rational numbers. In a similar way, we can, it is also countable. Then, so it is this is countable, is it not? And this, then set 0, singleton set 0 is a countable set, is a finite. So, if I take the all union, then set of rational number is set of all positive rational numbers, all negative rational numbers and including 0. So, if we put it in this form 0, 1, minus 1, half, minus half, 2, minus 2 and continue this way, plus minus and all these things, then this entire set is countable. 1 to 1 correspondence with that and countable. We can get this. Then also we were discussing about the points whose coordinates are rational number. This is another example that also we have seen. The set of points in a plane whose coordinates are rational numbers. Is countable. So, set of points in a plane whose coordinates are rational numbers, that is, the set is of this type whose coordinates are rational numbers. So, we can say A B, where A and B both are rational numbers. Q is the set of rational numbers, because any point in the plane will be ordered pair and we get this point. Now, this is each Q, since Q is countable, Q is countable set, and this set is a ordered pair of whose elements are countable. Then according to that result which we have seen, that if S1, S2, Sn are countable, then the countable union of the countable set is countable, and accordingly we can say if there is a n tuples, each coordinates belongs to a set which is countable, then that collection of the n tuples will also be countable. So, basically it is a double means coordinate, and where these are rational. So, this will be a countable set, is it not? So, we can say it is a countable. Actually, based on this result is that set of point based, since you can say the set of a set of points in p dimension, this is dimension is 2. in p dimensions, each coordinate of which which assumes a countable set of values is countable. In fact, this was shown already, because if suppose a set of p dimensional is there, we prove by means of induction. We have shown that if the set this set A1, A2, AP, where the AI's are in a set A which is countable, then this collection of the set is also countable, and this we have shown when I is 1, then this coincide with the set A which is countable. Then we have assumed for p say up to p minus 1, and for the p, when you write the point, it is of this form called ordered pair. Then when you fix up one value, other values keep on changing. So, it is a countable set. So, this we have already discussed, and this countable. Okay. Now, based on the another result, which is the set of polynomials that is a naught x to the power n plus a 1 x n minus 1 plus a n minus 1 x plus a n. This is the by where the coefficients, this set of all polynomials where the coefficients are integral coefficient with integral coefficients is countable. Means this set of polynomials where the coefficients are integers is countable. Now, you see there is a one-to-one correspondence between the set of polynomials and this set of p tuples, since there is a one-to-one correspondence with the set of points correspondence between the polynomial a naught x to the power n, a 1 x n minus 1 plus a n, let us be p x of degree n, to the tuples a naught, a 1, a 2, n plus 1 tuples. There is one, means corresponding to each polynomial we can get these tuples, and if this tuple is known, we can construct a polynomial of degree n. So, there is a one-to-one correspondence between these two. But what are the coordinates? But the coordinates of this, they are integers, integral values, and this integer is a countable set, which is countable. So, this collection of the tuples is countable set, because these integers and this collection of the tuples will be countable. So, this is countable, and there is a one-to-one correspondence between the elements of this set to this. So, this collection will also be countable. So, this shows that set is countable. So, set of polynomials is countable of degree say n is countable. It's okay. Then algebraic numbers. The set of all algebraic numbers, the set of all algebraic numbers is countable. What is algebraic number? The algebraic number x it is a solution of an algebraic equation. The an algebraic number x, an algebraic number x is the solution of an algebraic equation of the form a naught x to the power n a 1 x n minus 1 plus a n equal to 0, where the coefficients a naught, a 1, a 2, a n, these are all integers. So, this is the solution. A number x which satisfy this equation will be an algebraic number, or corresponding to a solution of this equation will be an algebraic numbers. Now, if we remove this 0, just I take, then this is a polynomial of degree n, and the coefficients are integers. So, according to the previous result, if the coefficients are integer, then collection of all such polynomials will be a countable set. Clear? So, once the polynomial, when we put it equal to 0, you are getting an algebraic equation. So, the roots of this algebraic equation will be at the most n. So, these n roots which will satisfy this equation. So, each equation will have the roots, and since this equation, this collection of the polynomial is countable, therefore, the corresponding roots will also, set of all algebraic numbers which are the roots of this equation will be countable. So, this we can say like this, we can write like this, since every polynomial equated to 0 has only a finite number of root. Number of roots has only a finite number of roots. Therefore, the set of all algebraic numbers, therefore, the set of all algebraic numbers forms a countable set countable sets of finite sets, because these are solutions are finite. So, it forms a finite set. So, it is countable and is consequently countable, and hence is countable, consequently countable. That is what, because this polynomial, when you find the roots of this polynomial, you are getting a finite roots, maybe at the most n. So, basically each equation correspond to a roots. So, we can just say that this equation has the roots, say alpha 1, alpha 2, alpha n, say alpha 1, alpha 2, alpha p, where the p may be less than or equal to n. So, this equation will correspond to this. So, the collection of all such equation means collection of all such elements, but these are finite, which is countable, okay, and then collection pth tuple is also countable. So, this set will be a countable set. Okay. So, okay. Then the algebraic numbers, once you get, then all the transcendental numbers becomes the uncountable. So, let us see the few examples of uncountable sets. First example, which is say very important, is the real set of all real number in the interval open interval 0 1 is not countable. is not countable. So, what the concept is that all the infinite sets need not be countable. So, this is one of the example where the set of all real numbers, these are they form infinite sets, infinite real numbers lying between 0 and 1, but this set is not countable. The reason is like this. We assume suppose the set is countable. Suppose the set of all real numbers, suppose the set of all real numbers in the open interval 0 1 is countable. So, once it is countable, we can arrange in the form of sequence. So, we can arrange them in the form of sequence. We can arrange the elements of this set in the form of sequence. Say suppose say x 1, x 2, x n and so on, because they are infinite numbers. So, we get a sequence, infinite sequence. Okay. Now, each x I, these are reals in the interval 0 1. So, we can write down the decimal expansion of x. So, each element, each x I will have decimal or can be expressed in a decimal expansion. Decimal expansion will have a decimal, can be expressed, will have a decimal expansion, or can be expressed by means of can be expressed in terms of the decimal expansion, in decimal expansion. So, let us suppose the x n is having the decimal expansion as 0.a1n, a2n, a3n, ann and so on, where what is a, where these coordinates, where the age, these age and these age are any one of the integer or any one of the digits 0, 1, 2 up to 9, a terminating, we assume is a terminating decimal being terminating decimal being supposed to end with a continuation of zeros. Means when the terminate, suppose it terminate here, then rest we will write 0 0 0 0 like that. So, it terminate 1. Okay. Now, with the help of this, let us construct a new number. So, now we construct a number alpha as follows. Alpha, I am writing the decimal expansion of alpha is 0 point alpha 1, alpha 2, alpha 3, alpha n and so on, where such that the alpha n is nothing but a n n plus 1, except that a n is 0, alpha n is 0, when a n n is either 8 or 9, in order to avoid the possibility of recurring 9 in it. This is done in order to avoid the possibility possibility of a recurring 9 okay, in alpha. This we are doing. Now, we claim that this point alpha so constructed differs from any term x 1, x 2, x n of the set of the points in the 0 1. Why? At least at one place. Suppose I take x 1, then x 1 here is a 1 1 is the first place, a 1 1, while in alpha the first point is alpha 1 and alpha 1 is what? A 1 1 plus 1. So, basically whatever the first point is, first decimal place is there, we are replacing this by plus 1. Next digit, the digit will be, say, instead of this we can write the 7 to 8, 6 to 7 and so on, except on whenever it is 8 or 9, then we can write this to be 0, that is all. Suppose this is 8, then we get 9. So, we will put it alpha 1 to be 0. Similarly, when to x 2, the second decimal place in x 2 is a to n, but second decimal place of alpha is alpha 2, which is a 2 2 plus 1. So, again 1 is added here. So, clearly we will see except. So, this number alpha is different from any one of the numbers x n. For it is different from x 1, in at least the first digit. It is different from x 2 in at least the second digit and so on. So, this way. So, but alpha is what? Alpha is having decimal expansion where the positive this side is 0, means all the terms are less than 1, lying between 0 and 1. So, it is, but alpha is a real number lying in the interval 0 1, and since we have assumed 0 1, the set of all real numbers in 0 1 is countable. So, it can be arranged in the form of the sequence that we have, but this alpha does not fall in any one of the does not coincide with any one of these x n. It means that our assumption is wrong, because if it is countable, then alpha must be one of the x n's, but this is not true. So, that shows that our assumption is wrong. So, contradict our assumption, hence 0 1 set of all points, hence the set of all points, all real numbers in the interval 0 1 is uncountable, is not countable, and that is proof. So, okay. Now, if we take, say, any interval, the set of real numbers in any interval a b is not countable, because if I make the function t minus a over b minus a, this is our f t, then it will transfer the function, this mapping will transfer the interval a b into the interval 0 1. Okay. And this is a 1-1 transformation, it is a 1-1 mapping. So, and this interval is uncountable. So, set of all points in this interval is set of all reals, in this interval is uncountable. So, in this also set of all real numbers in this interval is uncountable. And then if we extend it, then we say an important result is that is the set of the continuum is not countable. The continuum is not countable. Continuum means set of all real numbers over entire real line is not countable. Entire real line is not countable. That is what it. As a corollary of this, we can prove one thing: the set of irrational numbers in any interval is not countable. And solution is very, because a interval AB contains both rational and irrational points and irrational real numbers, reals. So, and rationals are countable. This we have seen. This is uncountable. Therefore, this implies that set of all irrational numbers in the interval AB is not countable. And same way we can also write this corollary: the set of transcendental number, which are not algebraic number, transcendental numbers in any interval is not countable. Because the reason is, if we remove the set of all algebraic numbers from this, then we obtained a algebraic number which is countable. We can get the transcendental left out, because the reason, if we remove the set of algebraic numbers which is countable, from the any interval AB, then the complement set of transcendental is uncountable. Then complement of it, then remaining one, which is transcendental number, will be not countable. And that is one. Okay. So, there are few examples we have seen. Now, few more we will continue when we go for the concepts of like some dense set, then perfect sets, etc. Then we will go for the few more examples where the countability or uncountability of the set will be considered. Now, let us come back to our metric space. Now, so this is the optional one, but we will discuss it here. As we have seen that in case of the real line, when we pick up the 2 point x and y, then the distance between x and y is defined as mod of x minus pi. This is the absolute distance between the 2 points on the real line, and this distance will always be greater than 0 and will be 0 if and only if the x equal to y. Then if we measure the distance either from x to y or from y to x, both will be the same. Then third is, when we take the any point z either in between x and y or maybe outside, then this will remain less than equal to x minus y plus y minus z. So, these properties are satisfied by the absolute function, or we say the distance function defined on the real numbers or on the real line. Then we wanted to extend it to an arbitrary set, because this is the set of real numbers. We are having this property. Now, this property we wanted to make it as an axiom for an arbitrary set, and that leads to the concept of the metric space. So, we define the metric space as a metric space x d is a pair x d consisting of a non-empty set x of elements, we call it a real point, call it points, and a notion of distance function d defined over x cross x to r which satisfies the following properties. The following properties. The first property is the distance between the 2 point p q is greater than 0 if p is different from q and distance between p is 0. In fact, other way around also we can say, vice versa also. So, second is distance is this, and d of p q is the same as d of q p. Then C is d of p q is less than equal to d of p r plus d of r q. So, distance function is we satisfy the first is, you can write thus 0 property. D is a non-negative real valued function, non-negative real valued function, and this property we can also write it, that is d of p q is 0 if and only p equal to q. We can replace it. In fact, this is, so when p and q are identical, both are equal to 0 and vice versa. So, if these properties are satisfied, then we say this set x together with the notion of the distance forms a metric space. And one of the example is our x is R set of real line and d of x y is defined x minus y, where x and y are real. Then as we have seen earlier, satisfy all the property. Then another examples is, suppose x is say R2. R2 is the 2-dimensional plane, where the elements is of the form say x1, x2, y1, y2 and like this, so on. So, suppose this is x element, this is another element and continue. Then d of x y, which is written as mod x minus y. I am writing just the same using the mod, but meaning of this is in 2-dimensional case it will be x1 minus y1 whole square plus x2 minus y2 whole square under root. In case of 3-dimensional, the distance between x y is defined as we write the same way mod x minus by, but thing is the is x1 minus by 1 whole square, x2 minus by 2 whole square, x3 minus by 3 whole square, means x1 x2 x3 by 1 by 2 by 3. These are the coordinates belongs to R3, y by 1 by 2 by 3 belongs to R3, and it can be shown that these D's satisfy the condition of the metric. So, we are not going in detail, it is a part of the function analysis. So, there it will be discussed. What we are concerned is that since we have discussed it, the concept of the neighborhood, open sets, closed sets, open ball, closed ball in real line with the help of the modulus functions. So, this we wanted to extend it, this concept to a arbitrary metric space, arbitrary set with the notion metric space. So, let us see the few say concepts which are useful for further. So, we define let X be a metric space, let X d, I am writing X d be a metric space, okay. And then we define like this. First definition is the neighborhood. Neighborhood which we denoted by N or P, that is neighborhood of a point P with radius R. So, this we write as a neighborhood, I am writing NBD, neighborhood of a point P in a metric space, in a metric space X d, in a metric space X d is the set of all points, is the collection or is the set of all points Q belongs to X such that the distance between P and Q is strictly less than R. Then R is called the radius of this, then R is the radius of the neighborhood. Okay. It means our neighborhood of a point in a metric space which we denote by NRP, that is the set of those point Q belongs to X such that distance of P and Q is strictly less than R. So, this in a, for example, in case of real line, if X is R1, then this neighborhood NRP is nothing but what? Q belongs to R1 such that mod of P minus Q is less than R. That is, it is an interval. It is an interval lying between P minus R to P plus R, and Q will be the point somewhere here. So, this is the interval equivalent to the interval this interval. When X is R2, then NRP which is Q belongs to R2 such that mod of P minus Q, the distance, I am just writing the distance, okay, D2 is less than, this is the 2, distance 2 is less than R. That is, it is the set of all Q such that under root of this, under root of P, 2 points are there, then P1 minus Q1 whole square plus P2 minus Q2 whole square is less than R. That is where P is P1 P2, Q is Q1 Q2, both belongs to R2. So, it is a ball centered at P1 Q1 with a radius say R. So, all such point will be here. So, this is the neighborhood of this. Similarly, we can go further. Then second definition is the limit point of the set. A point P in a metric space X d is a limit point, of the set E, which is a subset of X, limit point of the set E, if every neighborhood of P, if every neighborhood of P, if every neighborhood of P contains a point Q different from P such that Q is in E, So, this is the point and limit point, means if this is a space metric space X D and here is the set E, we say this P may or may not be belongs to E, but it will be a boundary point of E if it is a limit point. Then P is called the limit point of this if every neighborhood around the point, if we draw neighborhood, means suppose in R2 we get the neighborhood in this pair and like this. So, if every neighborhood of the point P must, if includes the point Q other than P which is in E, then we say P is the limit point of the set E. Okay. Then and definitions third, this is the definition about the isolated point. If P belongs to E and P is not a limit point and P is not a limit point, P is not a limit point of E, P is not a limit, then P is called an isolated point. P is called an isolated point. Isolated point. For example, suppose I consider the set E as this. Suppose I take set E as the set or say 0 1 union set 2. Suppose I take this set 0 1 union 2 in R2, which is subset of R2 R sorry in subsets of R. So, interval this. Now, 2 here 2 is an isolated point, isolated point. Why? Because if we draw a neighborhood around the 2, then it does not include any point of E. So, 2 cannot be a limit point of E, but 2 is a point of E. So, it is an isolated point. And C D. Closed set. E is said to be closed. E is closed if every limit point of E is a point of E, is a point limit point is a limit point of E. Then E, a point P is an interior point of E if there exists or if there is a neighborhood, if there is a neighborhood n of P, there is a neighborhood n of P with a suitable radius such that this neighborhood is totally contained in E. So, what he says is, this is our set E, we say this point P is an interior point. If there exists a neighborhood around the point P which is totally lies inside E, then such a point P is called an interior point. Then E is said to be open. A set E in a metric space is said to be open if every point of E is an interior point of E. Interior point of E. Then this called then G complement. The complement of E E denoted by E C is the set of all points P belongs to X, set of all points P belongs to X such that P is not in E. H. A set E is said to be perfect in a metric space X D if E is closed, and if every point of E if every point of E is perfect, if every point of E is a limit point of E. I, a bounded set we have already discussed. So, it is a set is said to be bounded if there exists or if there is a real number m such that and a point q belongs to X such that the distance between P and Q does not exceed by m for all P belongs to E. And lastly, we say J, a set E is dense in a metric space X D if every point of X is a limit point, every point of X is a limit point of E or a point of E It means what? When we say a set, this is X, a set E, this is E, is said to be dense in this. It means every point of X is a limit point of E or a point. So, if we take any point X, say here, suppose I take any point X here, then this point will either be a point of E, or if it is not a point of E, then it must be a limit point of E. So, limit point of means if we draw a neighborhood around the point P, there must be some point Q of E which is different from P. So, in this case the element of X and element E, they are so close to each other that you cannot separate out. As soon as you take any X and draw a neighborhood around the point X, you will always find some point of E different from this, or maybe the point itself is a point in E. So, such a case we say it is dense. For example, the set of real line, for example, our E, which is a set of rational number, and X is R, then this E is dense in R, because any real number can be approximated by means of rational number. So, if we draw any real neighborhood around the point real number, we get another real number is rational point which is different from this. So, this becomes the dense. Okay. Thank you very much.